Good morning. Uh, Today we have another chapter on magnetic uh, forces and fields. Chapter 27 was primarily on magnetic forces, and now we're going to look at where the magnetic fields are being generated. So how do we generate a magnetic field? Now the picture on the front of this chapter looks kind of like the last one. What we're doing this time is we're running a bunch of current through here. Oh, it is. It's the very same, huh? It's just a different shape. So we're getting a bunch of iron filings and having them line up. So that's going to be a solar. I have to remember that picture for the end of the chapter. But there's a magnetic field. Because of the presence of these currents, we're getting a magnetic field set up along this direction. And the little iron filings that have been dropped onto this surface are lining up with the magnetic field. All right, magnetic fields, where do they come from? Magnetic fields, which we learned actually in the last chapter, are a result of charges that are in motion. The most common example that we run into with generating magnetic fields is just to take a current running through a wire. Current running through a wire, hey, that's a bunch of charges in motion, and that's a very easy way to generate a magnetic field and to control kind of the shape or the geometry or the intensity of the magnetic field by controlling the direction that the current is traveling. Do we want to just use straight current? Do we want to have the currents looping around a bunch? Now for a straight wire, what we find, or what the textbook presents first, is to say that the magnetic field is generated and that it's proportional to the current and drops off. So this is kind of thrown out there as a beginning point. And then they also introduce this constant mu naught. Well, the constant mu naught that comes into these magnetic field formulas is actually related to the electric force constant that we've already been using. Now the value of mu naught is given here as 4 pi times 10 to the minus 7, but we'll take a look and see how that's related to something we've already done. So in any case, we're just gonna throw out one of these examples right away, or run through one of these examples. We're going to calculate the magnetic field surrounding this current. So what we're saying is that there's current, it's going along this wire, the wire goes on and on for some distance, and so we can treat it as a long straight series of charges in motion. We're going to come 10 centimeters away from it, point P, and ask, what's the magnetic field at that location? Now, it says that the current is 25 amps, it's constant. What's the direction of the magnetic field, and how large will the magnetic field be? Now, in the last chapter, we actually went through some of this, so let's re-familiarize ourselves with how this is working. I'm going to say this is point A instead of point P. Here is a charge. The charge is in motion, and what we said was that the charge is going to generate an electric field that's directed away from the charge, but it's also going to generate a magnetic field, and that the magnitude of the magnetic field, kq over r squared, same as the electric field. We put an extra factor of c out in front of the magnetic field, where c is our space-time conversion factor, the speed of light, 3 times 10 to the 8th meters per second. We said that the magnetic field, unlike the electric field, the magnetic field is going to depend on V over C, and that the direction is going to be these. Well, if it's a positive charge, it will be right-handed loops. If it's a negative charge, it will be left-handed loops surrounding the direction of the velocity. And then we pick up a factor of sine theta based on this cross product. So the idea is, if I have a current, the current is going to be a whole series of these charges, all in motion together, and so the magnetic field loops will then be very uniform at a particular radius, and the magnitude of that will be, now this is magnetic field depending on a velocity, and if we take all those charges and add them all together, and turn them into a current, we find out that's the formula we get. We're not showing the details of how that takes place. We'll show some details a little later on. But this is the magnetic field surrounding a charge. It has this angular dependence to it. But once we have a long, straight wire with current running through it, the formula becomes 2K. Little k is that electric magnetic force constant that we've been using since chapter 21. That has not gone away. We're still using that. That's gotten us through everything. The k now is divided by c squared. A couple factors of c here. There's a factor of the current, and it's 1 over r. So it's going to drop off like 1 over r. Individual charges, the field was dropping off like 1 over r squared, but now we have a lot more charges than we had before. Now, just for comparison, in the book, this formula is saying, or in the slides we just looked at, mu naught over 2 pi times I. What is this mu naught? And historically, there were two force constants. One was for electric forces and one was for magnetic forces. And electric forces and magnetic forces seem to be somehow related, but they were really thought of two distinct forces. And then somewhere along the way in the 1800s, it was realized that there was a simple connection between these two, and that electric and magnetic forces were both a result of charges in motion. And so it's still based on charges. And the epsilon naught and the mu naughts can actually be written in terms of, epsilon naught was used for electric force constants, mu naught was used for magnetic force constant, and then it was realized there's a simple connection between those two. And so mu naught is equal to 4 pi little k divided by c squared. And so I am going to stick with using little k. The textbook is going to be using, I think they're going to be using mu naught almost exclusively. And that's the conversion between the two. Again, I'm going to stay with little k because by using little k throughout, what that's going to help us do is see the similarities between the electric and magnetic fields. These are coming from the same sources. The formulas are going to look very, very similar if we use the same force constants for each. So that's my justification for being difficult with this and sticking with little k. And I'm encouraged that when I see some of the newer textbooks coming out, I still really like our textbook, but some of the newer textbooks out are sticking more with the one force constant for both. All right, here's the example that they gave us. Let's see, where is that? Here it was, 28.1. Now what we did is we took a little bit of a side trip here, and what we did was went through and reminded ourselves where these formulas are coming from. It traces back to individual charges. We don't want to start with a current. A current is a big, complicated thing with a lot of charges in motion. I want to start with one charge, and from that formula we can derive the others. So now, I'm ready at least, thank you for your patience, to be able to, oh no, that's their formula, right? Which is fine. Okay, so just to let us know how to make the connection here, we're going to start seeing more factors of c and c squared. C is the speed of light when you look it up, 3 times 10 to the 8th meters per second. But it's more fundamental. It's actually the conversion factor. We talked about this in chapter 27. C is actually the conversion factor between measuring distances and measuring time. So it's kind of, I think it's kind of amazing or kind of interesting here. 1 second of time is equal to 3 times 10 to the 8th meters. I always suspected that, right? That 1 second of time is equivalent to 300 million meters. Another way to look at that is that 1 nanosecond of time is the equivalent of 30 centimeters, which is about 1 foot. So 1 nanosecond of time is about 1 foot of length. That's weird to think about, but anyway, that's what this factor of c is coming in from. It has to do with special relativity and understanding how space and time are connected. Okay. So I'm going to work from this formula, which has the little k in it, and it has factors of c. Now when I put these numbers in, what I need to be aware of, and I didn't do it on this problem, 8.99 times 10 to the ninth is the number that we gave for little k. Well, c, if I look up c, is given as 2.998. Now it turns out that it's not a coincidence that 3 squared and 9 are more or less canceling out here. It actually has to do with the way that coulombs are defined. So coulombs, the unit of charge in standard units, is actually based on these magnetic measurements, measurements of magnetic force. And the coulomb has been defined in a way where the force constant divided by c squared is exactly 10 to the minus 7 newtons. What does that look like? Newtons second squared divided by Coulomb squared, something like that. So anyway, when we're doing these calculations, I don't want to put 8.99 in my calculator. I actually want to put 9 and let the 3 squared exactly cancel the 9, because that's an exact cancellation. I didn't do it this time. I hope when I was doing the numbers I put the 9 in. So anyway, 2 times k, the current that they gave us for this was 25 amps. The distance away from the wire that we're looking at is 10 centimeters. And when I did all the calculations, I ended up with 50 micro Tesla. Now what direction is that in? And the direction is going to be into the page. So I'm getting these right-handed loops around the current. The current is thought of as a flow of positive charge. The electrons are actually going the opposite direction. And so it's going to be right-handed loops for the current. If I think of the electrons, these are now left-handed loops because the electrons are going the other way. In either case, I'm going to get the loops going into the page on this side and then coming out here and circling around. So those magnetic field lines are circling this wire that's carrying the current. And the formula that we have here actually depends on the wire being very long compared with this distance of 10 centimeters. If this wire begins to loop a little bit, then this formula is not going to be exact anymore. And this is kind of the same problem, just done one more time. I ended up kind of duplicating this. Again, these are the numbers that went into the calculation. Here I did, just for comparison, we could ask, a magnetic field 50 microtesla, it sounds so small, but how does it compare with the electric fields that we've seen before? Well, I can convert the magnetic field so that it's in the same units. We talked about this too, that historically magnetic fields have been measured in different units compared with electric fields, even though they are basically the same thing. And so to convert the magnetic field so that it's in the same units, newtons per coulomb, I multiply by a factor of c. And then I can compare it with the problems we did back in chapter 21 and 22 and when we were looking at electric fields. And a magnetic field of 50 microtesla measured in newtons per coulomb would be 15,000 newtons per coulomb. So that's a pretty good sized field. Okay, so this magnetic field is not actually so tiny when we start putting it in units that match up with electric fields. Okay, here's another example we're going to look at. What it's saying is I have two currents. Now again, we got to think three-dimensionally on these. This current is coming out of the board. This current is going into the board. Current 1 is 5 amps, current 2 is 7 amps. They're going in opposite directions. Now, with the current coming out here, these are going to be right-handed loops. So the current's coming out here, and right-handed loops here are going to give me a magnetic field like these directions here, the directions of the arrows. This is going into the board, so if I use a right-hand definition here, the magnetic field loops are going the opposite direction. Now at a point between the two, and it looks like it's right halfway between, it's 5 centimeters from each. Those two magnetic fields are going to combine at that particular point, and we can add the effects together. We can take whatever B1 is and whatever B2 is, and we can add them together. And we already have the directions figured out because we've been doing this directional diagrams throughout here. Now the magnetic fields, let's see, I could come to this direction, or I could come to this location rather, and at this point the magnetic field from current 1 would be pointing this direction, and then if I looked at the magnetic field coming from point 2, that would be pointing off in some other direction. So this is not the only place where I could add those two magnetic field vectors together. It's just the one they happen to pick in this example. So if I pick that particular location, I'm going to write down all the information that was given. I've got R1 and R2. Fortunately, you know, this is perpendicular here. Fortunately, they've given me information where I could just add these two together. And we can see from the diagram the direction of the magnetic field. So there's my formula. These are two very long wires. And so I can use 2ki over c squared times 1 over r. 2k over c squared, that's a bunch of constants. I just need the two currents. I need the directions that the currents are traveling in. And I need the R1 and R2 values. Putting those in, I ended up with, now let's think, what were the distances? 5 centimeters. How big is 5 centimeters? 5 centimeters is like that, right? So I've got two wires that are separated by 10 centimeters, and I'm looking at a point halfway between, and those two magnetic fields, one of them is working out to be 20 microtesla, that's the one with the 5 amps, and the one with the 7 amps is working out to be 28 microtesla, and I can add those together. The combined magnetic field from both sources will be 48 microtesla. And remember, even though this is microtesla, if we convert this into newtons per coulomb by multiplying by C, that's going to be a large number. It's going to be in the thousands or tens of thousands of newtons per coulomb. Don't underestimate Tesla. All right, here is a conceptual example. So we're working a lot of these examples on wires that have current running through them. So here's another example. I've got 4 wires. 2 of these wires are running along here with the currents going into the board. And then I have 2 more coming out here with the currents coming out of the board. It says these are 4 long parallel wires. They're all running together for, you know, many, many meters. And they all carry the very same amount of current. 2 of these are into the page, 2 of these are out of the page. How are we going to get the magnetic field to be larger at the center of the square? So let's see. In this example, since I'm going into the page and I'm using right-handed loops, at that point my right-handed loop is going to give me a magnetic field in that direction. The magnetic field is going to be tangent to a circle that I've drawn around that current. What about 2? Well, sample 2 also going, so I'm going to draw a circle around source 2. Now, I'm going to put my thumb into the direction. These are right-handed loops. And that says at this point, the tangent line is pointing here. So 1 and 2 together, they partially cancel out. Their vertical components cancel, but the horizontal components add together. So I'm going to get a combination between 1 and 2. I'm going to get a net magnetic field here. Now what happens with 3 and 4? 3 and 4 coming out of the board. So when I do the circle around 3 and look for the tangent line in the right-handed direction, it's off in this direction, and from 4 it's here. When I add those together, they're not going to cancel, right? 1, 2, 3, and 4 combined. Vertical components will cancel, but the horizontal components are going to add together. So I'm going to get a net magnetic field in the horizontal direction, what we might be calling the negative x direction, by taking all the x components of those fields. Now what happens if we reorganize the directions of the currents in the direction we have over on the right? And here, when we go through and we sample the direction, let's just try one of these. So one is going into the board, and so it says that the right hand, oh, that hasn't changed. So the 1, magnetic field 1, is going to be the same in both diagrams. It's 2 and 4 that switched, right? So 1 and 3 are in the same directions they were before, but 2 and 4 are going to flip and be in opposite directions. And if all those currents are the same and we're right at the center between all 4 of them, we're going to get perfect cancellation. So at least at that one point, right at the center, all the magnetic effects from the 4 currents are going to cancel out. All right, what happens if we have 2 wires? Again, 2 long wires with current running through them. Here's current 1, here's current 2. How do we determine the effect that current 1 will have on current 2? And it's a 2-step process. The first thing we do is we go, okay, let's imagine I2 is not there yet. Let's just think about current 1 and the magnetic field that it's producing. So current 1 produces a magnetic field, and here it is. Here those blue lines are showing the right-handed loops of magnetic field that are being generated by current 1. Now that we've determined, let's see, so I think we have a picture that looks just like this. Yeah, so it's going to look just like this. I've got a current going in this direction, and I'm going to have a magnetic field going into the page on this side and then coming back out on the other side. So remember what this picture looks like, because that's what's happening right here. So these right-handed loops are circling around and going into the page, and that means at the location where current number 2, we're going to bring in current number 2 now, current number 2 is going to be running through the magnetic field that has been set up by current 1. So 2 is running through magnetic field 1, and as a result, current 2 will experience a force. So, and we can kind of, I guess we can figure what direction that's going to be. I can use a right-hand rule. Current number 2 is going in that direction. The magnetic field that it's passing through is going into the board. The force is going to be in this direction. So all along current 2, there is going to be a force drawing it over towards current number 1. Here's another view of that. Here's my own drawing. So here is current number 1, all by itself. Here is the magnetic field that has been set up. This dashed line is saying, you know, we're planning on bringing in another current and running it right along that dashed line. So, but first of all, here's the magnetic field. And the magnetic field formula, 2K over C squared, I1 over R. Let's put some numbers in. Let's say that the current is 20 amps, and that the distance here is 20 centimeters. So I plugged those in, carried out the calculation, and I found that at this location, right along there, the magnetic field is going into the board, and it has a magnitude of 20 microtesla. So we found out how strong the magnetic field is right along there and what direction it's oriented. Now, if I looked closer, the magnetic field would be larger. If I looked farther away, the magnetic field would be less. Right at that distance of 20 centimeters, which is every point along here, the magnetic field is going to be 20 microtesla. Now that we've got the magnetic field figured out, let's bring in current number 2. So current number 2 is running through that magnetic field, and the force on a current running through a magnetic field is given by this formula. The force is going to depend on how much current how large the magnetic field is that it's running through, and then what's the orientation. Now, the current is running in this direction. The magnetic field is directly into the board. That gives us an angle of 90 degrees. So that's a 90-degree angle that we're looking at. Now let's say that the length of the wires is 40 meters. That's a good long distance, right? 40 meters is like 40 yards, a little more than 40 yards. And so that's a pretty good distance that we're looking at. So I'll put that in for L. And the magnetic field that I want to put in is the one coming from current number 1. And then let's say this one also has 20 amps. So now I'm plugging into this formula and I'm ending up with 160 micronewtons. So not an especially large force. And that 160 micronewtons is spread over 40 meters. So it's not much of a concentration of force if I'm only getting 160 micronewtons spread out over 40 meters of length of wiring. But here, here are all the force vectors. I drew all these little vectors in. Those are all the forces along the length of the wire. Okay, so what did we find out? Well, we found out this. We found out if we have parallel currents, those parallel currents are going to attract. How did we find out they were going to attract? Well, we did the cross product to find the magnetic field, and then we did a second cross product to find the force. And you might be thinking, isn't there an easier way? And not if you're starting from the fundamental formulas. Now what we could do is we could derive sort of a general formula that works in these circumstances, but my recommendation would be when you look at this example and you go through, and I think there's an example related to this in the homework also, do it step by step and talk yourself through it. Because one of the important features here is, what would happen if we turn this around? We've shown that current number 2 is going to have a force in this direction. What about the force acting on current number 1? And because everything is set up so nice and symmetric, if we flip this around, we start with current 2, look at its magnetic field, and then bring in current 1, we should be able to show that the force on current 1 will be in to the right. And so both currents will be drawn towards each other. That's what we're showing here. Now again, they've got this force just listed at one location, but remember, what we're calling force is all along the length. So that force is spread out over the length of the wire. And what we just showed was that parallel currents, I1 and I2, going in the same direction, they're going to have forces that attract each other. The forces weren't very big, and the numbers we put in, 20 amps, that's a pretty good current, right? 20 amps is about the max that you would get through a set of wires in household electricity. And the distance between them, well, the distance was 20 centimeters, so they're not right side by side. There's a little bit of distance between these that we're looking at. Now, if I reverse one of the currents, so we're calling this parallel, and for parallel the forces would be attractive, but when we think about how everything was derived, we realize if we reverse one of the currents, either one, so that the currents are anti-parallel, the forces would now be repulsive. The currents are going to be pushed away from each other. Okay, so here's another example, very same thing, I guess. Force between two current-carrying wires. It says we got 2 wires. It's only 2 meters of length, and it's in an appliance. And the wires are only 3 millimeters apart this time, so the wiring is going to be much closer than it was in those other examples. And it says that it's actually running off of DC, and our appliances pretty much are all running off AC, at least when we plug them in. It says that it's running off DC, and it's 8 amps. So I've got 8 amps running along 2 wires. I'm assuming these are running in opposite directions, right? If it's the current going out to an appliance and returning from an appliance, I'm going to assume this is anti-parallel. So, let's put the numbers in. Now, it's the same diagrams we did before. So here is the setup. The currents are going in opposite directions. What we have found is that the forces will be repulsive. They're going to draw away from each other. This is, again, breaking it down into two separate steps. But by combining the two formulas that we used, we get a formula that says that the overall force of repulsion, this time, between the two currents is going to be given by 2K over C squared times current 1 times current 2 divided by the separation. Oh, okay. I put little r here, but I put d here. I got to decide which one. Those variables need to match. They don't right now. And oh my gosh, and then instead of L, I put little l. All right, I didn't get my notation to match. So anyway, my intention here was that this L is this L. And that's not always the case. So, I apologize for not having these match correctly. And this D is really this little r. So here is 2. Oh, look, that should be 9. I still got the 8.99 in there. Divide through by C squared, divide through by the separation distance R. Now the R here is center to center. So let's be clear about that too. The R here is not surface to surface for the wires. It's center to center. The magnetic formulas that we've used are center to center of the wire outwards is what R is keeping track of, not from the surface. And so I put in current 1, current 2, and the length of the wire. And what it says is, over this 2-meter length, I'm getting a force of 8.5 millinewtons. So now the force is bigger. I mean, the other one was like 40 meters long. So bringing these two, these were so much closer, right? They were 3 millimeters apart instead of being, what was the other one, 200 millimeters or something? So it's about 100 times closer, and we're getting a larger force. The currents aren't especially large. I think the currents were larger last time, right? Anyway, we're going to get a force that's significantly larger thanks to the wires running nearby each other. Okay, so a bunch of examples looking at the magnetic fields set up due to long straight lengths of current is what we've been looking at. Let's move on to a different technique. So the way that we solved those problems before, actually the formulas that we were using actually involved different types of integration. We'll see some examples of that at the end of the chapter, just to show you guys where the formulas are coming from. So we're going to move on and use a different approach, an approach that is called Ampere's law. Now, do you guys remember Gauss's law from chapter 22? We used Gauss's law. We integrated over the surface of volumes and were able to relate the electric field to the amount of charge contained inside the volumes, and that was very useful to get formulas for the electric field surrounding spherically symmetric distributions of charge. What we're going to do with Ampere's law is similar. Well, let's see how similar it is. So what we've got is a current running through here. Now, up until now, let me see if we have a better picture here. Okay, I want to start with this picture actually. So I have a current running through here, and we said that the currents are going to end up with these right-handed loops, and that if the wire is long and straight over a long distance, these loops will have kind of a uniform magnetic field, a roughly constant magnetic field, all the way around the circle. Now the magnetic field lines follow a circular path, so they're not following a straight line, but the magnetic field has the very same value along that path. So what we do is we integrate over the length of that path. See that integral sign with a circle on it? Back with Gauss's law, that circle was saying integrate everywhere over the surface of a sphere This time, it's not a two-dimensional integration, it's a one-dimensional path integration, and what we do is we integrate along the path. And just like last time, with Gauss's law, this is going to impress your friends. So your friends are going to say, what are you doing in physics? And you're going to say, I'm doing Ampere's law, and they're going to say, show me some of the formulas, and you're going to show them this formula, and they're going to go, wow, that's impressive. Okay? But you will know that the evaluation of this integration, we only use this in situations where we have a lot of symmetry. We only are going to do these integrations when the integration is, I don't want to say trivial, but where the integration is fairly simple. So the integration here comes from saying the magnetic field is constant. I'm going to drop the dot product because the magnetic field is following the circular path that I've outlined. So I get to drop the dot product and drop my vector signs. The magnetic field is constant, so I can bring the magnetic field outside, and if I integrate all along that circular path, that is going to give me the circumference. It's going to be 2 pi r. So when we're using Ampere's law, and this is one side of Ampere's law, when I evaluate this integration, what it is always going to be in every example we look at, and we're going to look at 2 or 3 examples, it's not a lot, it's going to be the magnetic field, a constant magnetic field, times some kind of a length. For the example at hand, the length is a circumference, and so evaluating that integral is b times the circumference 2 pi r. Now what Ampere's law says is if I find a region where there's a magnetic field, I bet that's due to a current running through a wire. And so what we do is we relate this magnetic field to the current. Now the book is going to use mu naught times I, and I'm going to use 4 pi k over c squared times I. But it's going to work out as we did the calculation before. So this is actually one of the methods we can use to come up with the formulas that we've been using. Over here it says that if I now take, this is what Ampere's law looks like, that starting point. And what it says is when I solve this is for a long straight wire, the magnetic field surrounding it, the wire with current running through it, will be mu naught times I divided by 2 pi divided by r. That's the formula we've been using, and this is one of the ways to derive that formula. Now, Ampere's law depends on a lot of symmetry, the same way that Gauss's law depended on a lot of symmetry. In order to say that the magnetic field is constant, I have to be able to look at this diagram and say from every point that I look at around this circle, that has to in order for the magnetic field here to be the same as the magnetic field here, this current can't deviate to one side or the other. If I had the current deviating over here, that would reinforce the magnetic field. If it was spreading out over, if the current turned and went this direction, that would reinforce the magnetic field on this side. So in order for the magnetic field to be a constant value along the entire path of that integration, the current can't go to one side or the other. Well, at least it can't until it gets very, very far away. So in the limit of where this line of current just goes on a long, long ways, and this goes a long, long ways in the other direction, this formula will work. So as long as I'm close enough to a wire so that it looks like it's really, really long from that vantage point, this formula will work. Now I'm going to go back to that scary picture. Okay, this terrifies me. What Ampere's law says, okay, so this is Ampere's law right here that says that integrating the magnetic field along a closed path surrounding some current, the integration of the magnetic field along that path is equal to mu naught times the enclosed current. So it's how much current was enclosed by the path. So what this picture is showing is Ampere's law works no matter what crazy path we come up with. You can come up with a crazy, crazy path. Ampere's law still holds, but it's not practical to use because nobody's going to want to go in and try and carry out this integration. So just like Gauss's law, what's going to happen is we're going to end up using Ampere's law only in situations where we have enough symmetry that we can guarantee the magnetic field, the B field, is uniform along some length. It doesn't have to be uniform along the entire path, but it has to be uniform at least along some portion of the path that we're integrating. So in this one, it's constant all the way around. So this is maybe the easiest example. Okay, and that's the formula we've been using. So here's my own version written up of Ampere's law. I have my own notational preferences. I prefer using ds over dl. That's what I've learned in most of the calculus courses that I've taken, and actually most of the physics courses that I've worked with. At some point, maybe I'll get convinced to use dl, but I'm going to use ds. But other than that, and the ds here is representing little short distances of the magnetic field path. So I'm integrating along the path. Now the other item that I've changed is instead of using mu naught, I'm going back and using 4 pi k over c squared because if I only have one force, I only need one force constant. And I don't want to complicate my life with more than one force constant. You guys are welcome to use the mu naughts. I'm going to go ahead and keep using the 4 pi k over c squared because again, I think it gives us insight into how the electric and the magnetic forces and fields are related. So B times the path length, 2 pi r, is equal to 4 pi k over c squared. That's just a bunch of constants. And then this is the enclosed current. That's the formula, and that's analogous to the one that we saw in that previous example. All right. All right, let's take a look at a more involved, a more complicated example of all this. Here is a wire with current running through it. Here's current I. Here's a wire. What we're going to do now, which we haven't done before, is we're actually going to ask a question of, well, sure, we have a formula for the magnetic field outside the wire, but what's the magnetic field inside the wire? What if I actually go inside the wire itself? Now, depending on how the wire is set up, there's the current running through the wire will tend to spread out so that the current density is uniform across the cross-section of the wire. So we're going to get the current spread out uniformly throughout that cross-section. Now what Ampere's law does is Ampere's law provides us a way to go in and say how large will the magnetic field be as a result. Now what we're expecting is, let's think about this, if we get these circular paths and they shrink down to where they are enclosing less and less current. This is the same idea we had with Gauss's law. This time what we're saying is, if I'm looking at regions inside here, and I want to calculate the magnetic field, I only include the effect of the current within that Amperian path. It's not a Gaussian surface anymore. It's an Ampere's path. And I only want to include the portion of current passing through that smaller circle. By the time I get right to the center, the magnetic field is going to be zero. Okay, right at the center, the magnetic field is going to have to drop to zero due to symmetry. And as I get closer and closer in, I don't have to include these outer regions. So what Ampere's law is telling us is those outer regions, the contributions of the magnetic field from the outer regions will completely cancel within that dashed line. So what are they asking us to do here? Let's see. We're looking at points outside. Well, we've solved for that already. And then we want to look at points inside. We haven't done that yet. So that's going to be our new project, is to get the magnetic field inside the wire itself figured out. And then what they want us to do is whatever formula we come up with, they want us to plug some numbers in. Ooh, 60 amps. So this is going to be a, oh, that sounds, I think we're going to overheat this wire. So this is like a oh, that's not bad. 2 millimeters of diameter, that's actually pretty good. So that's probably a pretty thick wire. It's got a diameter of 4 millimeters. 60 amps, maybe it's going to be okay. Maybe it's going to be, I mean, this is like something going to an electric range, right? Electric ranges mostly are designed for something like 50 amps. Clothes dryers, maybe 30 amps. So this is a good size, this is a pretty thick wire. But I don't think it's going to overheat. And we're just measuring the magnetic field anyway. All right, so this is what the wire looks like. We're going to take a short segment of it, and then if we turn it and flip it so we can see the cross section, it looks like this. And if we need to, we can go back to their drawing, which was done a little more carefully. So what I'm going to do is, I'm going to take the outside region and say that when I carried out Ampere's law, I'm always going to get B times 2 pi r for these circular paths. So that's just going to get repeated. And so B times 2 pi r is equal to 4 pi k over c squared times I. And then what I've done with the magnetic field formula, I've divided through by 2 pi r. I canceled out the 4 pi. I'm left with a 2 ki over c squared, 1 over r. There it is. That's the formula that we got for a long current carrying wire. And that's outside. So outside it's behaving like 1 over r. Now what happens inside is actually a little more complicated. And so let's check time here because we're good. I think we can wrap up, I think we can finish up this example. So if I'm looking at regions inside, then I don't want to include all the current. The current that I want to include is only the portion inside that area. So if I think of that as a ratio of cross-sectional areas, pi over r squared would be the total cross-sectional area of that wire. That's a circular cross-section. If I'm looking at the magnetic field in here, Ampere's law is telling me only to include the portion of the current that's passing through pi little r squared. So let's say that little r is 1/2 of big R. If little r were 1/2 of big R, then the area that's enclosed in there would only be 1/4 of the total area. I would only be including 1/4 of the current. So, so I'm going to put that ratio in here, and this time when I carry out the formula, and you can see the formulas, the derivations look very, very similar. The left side of the formula, in both cases, is B times 2 pi r. That doesn't change. The difference between the two sides is when I'm outside the wire, I am enclosing the entire current. When I'm inside the wire, asking what the magnetic field is in these regions, I only include a portion of it. So I get that extra factor of little r squared over big R squared, the pi's cancel, and the formula that I end up with looks just like the formula over here, except that it's got a little r squared over big R squared factor. Now I rewrote it this way. I plotted these. And in some sense it's kind of backwards. This is the inside region. This is the outside region. I'm going to start with the inside and say if I start right at the center, the magnetic field right at the center is 0. And then it rises linearly. So the magnetic field rises linearly until we reach the edge of the wire where we're at a distance of big R from the center. And then I switch over and use this formula, and from there it's going to drop off. Now, what is the magnetic field right at the surface of the wire? Well, that formula I can get by setting little r equal to r, big R. That will cancel out, and the two formulas match when little r is equal to big R. So little r is my variable. Big R is the radius of the wire. So let's look at that a little bit more. So again, the outside formula could be rewritten as 2ki over c squared big R over little r. An outside region has the same set of values here, but it's little r divided by big R. Now, what we have outside here, 2ki c squared over big R, that's the magnetic field at the surface. So I thought, given what these two formulas look like, let's go ahead and evaluate the magnetic field right at the surface. And the magnetic field right at the surface, I can use either formula for that. I plugged in, I finally put in 9 for K and 3 for C, so that the 9 cancels the 3 squared exactly. And I put all the other numbers in. This worked out to be 6.0 10 to the minus 3 Tesla, or 6 millitesla, and that's right at the surface of the wire. So that's kind of a useful number to think about, because what we've got going on here is, well, it's a fairly, it's a 60 amp current running through a 4 millimeter diameter wire. And 4 millimeters is a pretty thick wire, almost half a centimeter. And so millitesla is pretty good sized. So that's a pretty good sized magnetic field that we're getting. Now in the problem, what they ask us to solve for, they picked these distances. They said, what's the magnetic field at 1 millimeter from the center line, 2 millimeters from the center line, or 3 millimeters from the center line? And for 1 millimeter, they've got the formula, they've got the graph here too. The radius of the wire is 2 millimeters, so 1 millimeter, sorry. 1 millimeter would be halfway between the center of the wire and the surface. So what's the magnetic field halfway out? And that's a linear relationship. So whatever the surface value is, if we're halfway out from the center, we'll be at half of that value. Now for outside, the 3 millimeter measurement is going to take us beyond, the 2 millimeter measurement is going to be right at the surface, and the 3 millimeter measurement is going to be outside. So what we're going to get is 1 millimeter is here, 2 millimeters is here, and 3 millimeters is here. The largest value is right at the surface. And then when I look at the formulas, inside, at the 1 millimeter mark, we're half of the value, this is at the surface, is 6 millitesla. Halfway out, we're at half the magnetic field, 3. And then when we're out at 3 millimeters, for that, I need to use this formula. That is going to be 3 millimeters divided by 2 millimeters. 3 over 2 is 1.5. And, or I'm sorry, I've got it backwards. This is 3 millimeters, this is 2. This is going to become 2/3. So this was 1/2, and this is going to become 2/3 of whatever the surface value is, and 2/3 gives us a value of 4. So that matches up with the graphs pretty well. So it's a good example, right, using Ampere's law. All right, I'm going to stop there because it's time for a break. So let's take that break. And you guys have any questions, let me know what questions you have.